All right, so in this chapter, 7.1 is all about area. We are going to eventually move out of area and onto volume. But the better you understand this area stuff, it has to do with geometry, but it still is calculus. And yay, this is the last chapter for the year. But hold on, I'll answer that at the end. Okay, so if we're going to find area under a curve, what calculus concept do we need to use? Integration, okay? How did we estimate area before we knew how to integrate? What did we do? Riemann sums, and then we learned how to integrate. All right, so what I want you to think, and this is where we're going to use the highlighter. All right, I want you to highlight this little section right here. I want you to highlight this. The area that is trapped between these two curves that kind of look like parabolas, but I'm not 100% sure. It does kind of look like a goldfish, and these two vertical lines. So go ahead and highlight that little area right there. Oh, look behind that. I already moved it. Okay. So we're trying to find this area. We have not done this yet, but really, you have enough knowledge to figure it out. So let's figure it out. How would we use integration? How would we kind of tweak what we know to solve that area? What was that? I just didn't hear you.
Bounds.
Bounds? Okay, so what are the bounds in this problem? A and B.
Would you have to
We're going to integrate.
and then add them together?
So we are going to need, we have two functions, so there's an idea of two integrals here. Add or subtract. Do you guys remember this problem in geometry where it looked like a picture frame? And your teacher said, find this area. You're going to do this all the time in real life. I'm just kidding. All right, how would you find the area of this picture frame? Find the big area, subtract out the parts you don't want. We're going to use that same concept here. So look what I'm going to do this. I'm going to use a lot of colors today. It's my promotion of the color run on Saturday. It just happens to fit the lesson. So this red part right here, how would you represent that integral? Integral from A to B. So we started x equals A, we ended x equals B. And then which function am I going to integrate? F or G? F. And then we put dx at the end of integrals, right? We should anyway. Okay, so that's more than I want. That's too much. So I'm going to switch color now. And what if I just integrated this part down here, the part I don't want? What would that integral be?
Integral from A to B.
Still A to B, same bounds, of the other function, of the g function. So g of x, again, dx. So what am I going to do to these two functions in order to find just the yellow part? Subtract. That's what we want to do. And in fact, I can even put this into a single one. I can just make it a single integral from A to B of f of x minus g of x dx into a single integral. And I'm going to write this off to the side here. What we really ended up doing was kind of doing left to right and then top minus bottom. Okay, look down at the bottom of your notes. Do you see anything? I'm kind of shorthanding it up here, but do you see anything like that at the bottom of the page? Okay, so that's generally how we're going to do these problems. Now, that's when the equations and the problem is set up with respect to x, which is, by the way, the only types of problems we've been doing. If we've been doing any other letter, it really was just a placeholder for x. Okay, so if you look down here, this is what I'm talking about. Whoops. This says with respect to x. That's what we're used to. So this, with respect to x problems, I don't think are going to be that difficult for us. The other ones, newer. We'll get more used to it, and I'm going to talk about that. But let's do a let's do an actual example. Then I'll talk about this whole with respect to y thing. So I actually want you to turn the page to this worksheet. This is going to be tomorrow's worksheet. Tonight's homework is going to be some book work, just a few basic problems. And then there's this worksheet, and we're going to do some of these in class today. Well, probably only one in class today, and then a few more tomorrow, and it'll all be due Monday. So for each of the following problems, the first thing we're going to do is sketch the region enclosed by the curves. So this is why we did that whole parent function thing. All right, so do you know how to graph y equals x plus 1? Yeah, it's a line. The y-intercept is 1, and the slope is 1. So I want you to graph this and be as accurate as you can be. The more accurate the graph is, the easier these types of problems will be for you. If your graph is super sloppy, it's only going to make things more difficult for you. And if I can do a neat graph on this air slate, you can definitely do one on paper. Use a ruler if you need to. Okay, so there's that line, y equals x plus 1. All right, what about this next? What's the parent function here? Yeah, we are on page 2, just making sure everybody realizes where we're at here. We skipped something. We'll come back to it. So it's a parabola. What do we know about this parabola? It's facing or opening down. What is the 9 doing? It's the y-intercept, and it's moving up 9. So I know the parabola looks something like this. Now, we need to be more accurate than that. So you can either do the whole over 1, down 1, over 2, down 4, like squareds. 1 squared is 1, 2 squared is 4, all that. Or we can do a t-chart if we need to. And I'm going to go ahead and do that on this one. I don't think everybody needs this on this problem, but there's going to be some other ones that are a little bit harder to graph where we're going to need a t-chart. So you could plug something in like 1. What's 9 minus 1 squared? Y'all can do this. This is algebra 1 right here. 1 is 8, so 1 comma 8. What if I plugged in a negative 1? Would I still get 8? Yeah, there's some symmetry there. Okay, what about happens if you plug in 2? You get 5. So this is where you kind of have to recall that stuff you learned before you came into this class. All right, anybody know the x-intercepts? Negative 3 and 3. And so this is a very neat and tidy parabola. The neater your graph is, the easier the next part will be for you. If you make your graph really sloppy, it's only going to make your life more difficult. So strongly suggesting you use a pencil here and not a pen. Okay, now if this was it, if there wasn't anything left, you would actually have to find the intersection points. And they're not pretty points on this problem. So this would be where we would want to use a calculator and either solve the equation where these two things equal each other or actually find intersection points. We'll talk more about that tomorrow. All right. There are 2 other ones. What shape do those things make? A line? What type of line? Don't say straight. All lines are straight. Vertical. Hoi vex. Okay. X equals negative 1. Vertical line. If you accidentally thought this was a horizontal line, it would really throw everything off and probably make the problem even more difficult. Okay. So the next thing is we've got to figure out what is the shape. Not the name of the shape, but where is it? Where is the part of the graph that's enclosed by all 4 of these things? And it's right here. And this again is where you could use a highlighter. And I think a highlighter is nice because unlike this air slate, you can still see the grid and the numbers underneath a highlighter as opposed to using a pen. But that's preference. This is just for you. Okay, we're trying to find the area of this piece right here. Okay, couple of things. We know the answer should be positive. Okay? All the answers, by the way, to these should be positive. Because you are truly finding area. If your answer is negative, you did something wrong. Okay, a volunteer? It's really easy.
You get a lottery ticket?
Sure. Okay, go ahead.
Oh, wait, is it a question?
Yeah, it is a question.
I'll do it.
No, I'm gonna make you do this. I want you to count all the blocks and estimate the area. Okay?
For a lottery ticket?
Yeah.
Well,
Count the block?
Life isn't fair. All right. So, for everybody else, while he's counting, we're gonna actually really find this. Okay? So, using what we did before, okay, we need to integrate left to right. Okay, so think about what are the x values, because this is a problem that's with respect to x. By the way, that's all we know how to do right now. We haven't even done with respect to y yet. So I want to know what is the x value where you start and the x value where you end. Those are your bounds. So what are those numbers? -1 and 2. All right. Okay, what do you think? Approximately 19? That's pretty close. It's not a whole number, so there was no way you'd probably guess it exactly.
why am I getting 15?
All right, -1 to 2. So remind me, and I'll give you a lottery ticket at the end. All right, -1 to 2. Those are your bounds. Keep in mind, those are x's. It's where you start and stop, and make sure they're in the right order. Okay, then we see this whole thing, draw a typical approximating rectangle. So we already kind of discovered like what we need to do, but I want to explain it again in a different way. So those of you that are more visual, I think this will help you. All right, I'm going to draw a vertical rectangle. And how do you find area of just one rectangle? Base times height, length times width. Okay, so what would the height of this rectangle be? How would you figure that out? Well, I kind of went above the blue line, but that's okay. It'd be wherever the y value is on the parabola minus the y value of the line. Okay? So, in other words, any given rectangle, like if I slid this over a little bit, that, that rectangle's height would be the top curve, which is the parabola, minus the bottom curve, which is the line. That would be the height of any given rectangle. And the width would be represented by dx. What does d mean? And what I mean here is not derivative, but what was the Greek letter we used? Delta. And what does delta mean? Change. So it's change in x. It's basically like x2 minus x1. Okay? And so that's why we have a dx there. Okay? So this may help some of you understand why we have to have dx there. So it's base times height. That's for one rectangle. The integration symbol with the bounds, what that does is it slides that rectangle all the way from the left to the right and it adds up all the rectangles to give us the total area. All right. Now, in the directions here, when you're doing these, all the odds, you're going to have to integrate by hand. All right. But we're together right now, so I'm going to let you use your calculator. So go ahead and get your calculator out on this one. This one wouldn't be too bad to do by hand. You'd probably want to distribute that negative and then combine like terms and things like that. All right, so remember you're going to integrate by hitting F3, option 2. And then we're just typing this in. After the comma x, what order should I type these numbers in? Comma, -1, comma 2. And we get 39/2. If you wanted a decimal, you just do diamond enter. And we get 19 1/2. Yeah, he was really close. That's the best estimate today from my other classes, so good job.
Yes.
Okay, you can write 39 over 2 or 19.5. Okay, would you rather integrate this by hand or the calculator? So make sure your calculator has working batteries and you're bringing it every day, because if not, you're going to be doing a lot of these integrals by hand. Okay, so this is pretty much a standard problem. There's nothing weird about this problem. We did have to graph a little bit, but there wasn't anything weird about it, right? Okay, some of these are going to be a little weird. All right, so turn back to example 2. Whoops, back to the very first page. So if you look at this example 2, they do give you the graph, which is nice, but what's weird about it, first of all? The sideways parabola, which is not a function. Okay, and I'm going to ask you again in a minute something weird about this. But we need something else, because this problem right here is not conveniently done with respect to x. Okay, and the y squared is going to be our big indicator as to when we need to do something different. I'm going to do this problem 2 times. If you just want to watch the first time, I'm going to show you using what we know right now how to do this, and it's going to get really messy. Then I'm going to show you something new that is a lot easier for this problem, but I want to show you why we even need to do it. And you're going to see we're going to get the same answer. Okay? And so if all we knew was with respect to x, which is true as of right now, we did derive with respect to time when we did related rates. So we have done some other things, but for the most part, this is what we've done. Okay, first off, I need this y squared to just be y equals. I need to square root both sides. So think about what would happen. If you square rooted 3 minus x, it's just square root of 3 minus x, and that is actually only representing that part of the parabola. It's a square root, so we are going to need plus minus. I'm going to go ahead and label this, and again, I'm going to show you one way and then I'm going to show you a second way. You may just want to watch this first one and not even write it down. Up to you though. Okay, this bottom part would be the minus part. That would be y equals negative root 3 minus x. And so kind of annoying. If we don't have to do this, maybe we won't want to in the future. Okay, the line, I'll do this one in green. That one's this graph right here. Okay, so we remember we want to find the area of this shaded piece right here. Okay, the next thing that's kind of strange about this, all right, is if I try to do the integral left to right, remember we want to do x values, it's clear that I'm starting on the left at -1. Where does this graph finish at the right? At x equals 3. But when I start to do top minus bottom, do you see how the line is the top graph? And then it changes. What the top graph is changes. That means we have to split it up into 2 pieces. All right, so I'm actually going to stop at 2, and I'm going to have to do something, and then I'm going to have to add on a second piece. So I have the line, that's the top function, x minus 1, and then I have the bottom part, which is negative root 3 minus x dx. Okay, everything's in terms of x. Then I got to add on a second piece, which is going to be this area right there. Okay, that's going to start at 2 and end at 3. So those are going to be my bounds. And on this one, the top integral is going to be the positive root 3 minus x, and the bottom one's going to be negative root 3 minus x, again with the dx. That's a lot of work, and it's really messy, and if you had to integrate this by hand, it would be really messy, because you're going to have to do u substitution and some other stuff. I'm going to spare us all from this, and I'm going to go ahead and tell you that the answer is 9/2. And now I'm going to do a problem a different way. What do you think the other with respect to is? With respect to y. Okay, so this you do want to write down. So if we do the problem with respect to y. And does anybody remember what I told you was the big indicator as to probably why we would need to do it this way? Because of the y squared. We need to get x equals. I'm actually going to have to scroll up here. Okay, this is what I mean. If y squared equals 3 minus x, what is just x equal to? Negative y squared plus 3, or we could say 3 minus y squared, which makes a sideways parabola. And that actually makes this whole parabola. I don't have to have two pieces here. The whole horizontal parabola is represented by x equals negative y squared plus 3. Okay, we also need to change the line, because if this is going to be with respect to y, then I need all the equations as x equals something in terms of y. So what would x equal in this part? Y plus 1. We're not used to seeing lines like that, but we have to do it this way. Okay, so that's this part right here. And I'm going to actually write these on the graph just to... We probably won't do this every single time, write it on the graph, although you could. So the shaded part is the same shaded part. So I already know what my answer should be. I should still get 9/2. And in a minute, once we write the integral, then we're going to actually type it in and figure it out. Okay, now when you do with respect to y, you got to pick y values. So we're not going to go left to right. What do you think we're going to do? Bottom to top. So what is the bottom and the top y values?
-2 to 1.
-2 to 1. So I even circled them here on the graph. -2 to 1. And instead of doing top minus bottom for the body part here, I'm actually going to do right minus left, because the right function is like the more positive function. So this is in terms of y. This is, you know, WHY. This is why we had to do this, because with respect to y means everything is in terms of y. So that's the right function. And then the left function would be y plus 1. And then dy, exactly. So notice that before everything was in terms of x, here everything is in terms of y. Okay, so besides the setup, which is new, and we're going to practice more tomorrow, which integral is easier to do? The bottom one, okay? Even in your calculator, it's easier to type this bottom one in than the top. You're going to have lots of parentheses and all that business. That's not what I meant to do. Here we go. And you can use, you know, y here if you want. So you can do integral, negative, and then just pick y instead of x. It is important that you have those parentheses after the minus. And then since we typed in y, we need to go comma y. That's kind of like the dy part. And then comma. Always make sure that the lower number is first. I know sometimes before I gave you integrals where these numbers were switched up. That should actually never happen in this chapter, because you're setting up the integral. So as long as you're correctly doing left and right, top and bottom, you should always get a positive answer here. Oh, did anybody catch? I messed up here. I didn't hit the caret button hard enough. And it's going to turn it into pretty print, so it's pretty easy to figure out if you typed it in correctly. And we get 9/2. 4.5. Okay, if you get a negative answer, you messed up something. You switched your bounds, or you switched the functions or something. All right, now before I end the lesson today, I want to talk about that rectangle thing. Okay, remember here on the problem we drew a vertical rectangle on that example 1 on the worksheet? What type of rectangle do you think I could draw here? a horizontal rectangle. Some people, this really helps them understand it, and some people, this is like nonsense. So I realize that for some of you, you understand how to do this without me explaining the rectangle. For some people, though, it really helps them understand what we're doing. Okay, so when you're doing with respect to y, you are going to draw a horizontal rectangle. And what that means is, this is like the base and the height of that rectangle. The base would be the difference of the two functions, okay? The right function minus the left function. That would tell you how wide any particular rectangle is. And the height would be dy. Sometimes this dy is, or dx even on the other one, is represented as the thickness, but it's the change in y. So it's like base times height. That's what we're doing here. That's how you find, it's basically one rectangle. And if you integrate from the bottom to the top, you're adding up every single rectangle like an infinite Riemann sum. So that's where, if you see this whole vertical, horizontal rectangle business, that's what they're talking about. If that doesn't help you, then you don't have to draw that on the graph. If it helps you, though, then make sure you do draw it. Keep in mind, this is day 1. We have more to do. We have more difficult examples to do. So if you're getting everything, that's good. But don't try to shortcut the answer, because that's not going to work on some other problems that are more difficult. Okay, your homework is, this, by the way, is just kind of like a recap of everything. This bookwork are some more basic type problems. That doesn't mean easy, I just mean more straightforward. The worksheet has some pretty weird examples. We're going to do more of those tomorrow in class. I'm not teaching you anything new for the rest of the week.